Hello everyone, hopefully you're doing well. In this video, we're going to continue with chapter 6, normal probability distributions. The focus will be mostly on section 6.3, sampling distribution and estimators. What we're gonna do is to see how to develop the ability to describe a sampling distribution of a statistic, and we will determine whether a sampling statistic serves as a good estimator of the corresponding population parameter, as we do for every single section. So the first step is to see the key concepts of the sections. We consider the concept of a sampling distribution of a statistic. Instead of working with values from the original population, we want to focus on the values of statistics, like sample proportion or, sample means obtained from the population. You know, so we're gonna show you a few of tables because in terms of concepts. Oh, sorry, there's a chair. Oh, it's changed. Okay. Um, right. So what we're gonna do is, most of all, is showing you some tables, and we will see how that goes. Now, you know, general behavior of sampling distributions. When samples of the same size are taken from the same population, look at these two properties. First of all, we would consider that sample proportions tend to be normally distributed, and the mean of sample mean is the same as the population proportions, right? So what we mean by that, like, you know, among the population of all adults, for example, exactly 70% do not feel comfortable in, suppose, that's a story, suppose that among the population of all adults, exactly 70% do not feel comfortable in a self-driving vehicles, we can see this, we can look at it as 70%, okay, of do not feel comfortable in self-driving vehicles. So what is the percentage of those who feel comfortable of doing it? So we can take a sample from this. It's already a sample taken from a population, but we can also take another sample. So, but let's explain better the behavior. All right. So the implications of the preceding, the properties we just tells you will be extensive later. But now, look what happened. Proportions. Remember proportions? The way it works, if you have a sample, let's say you take a sample of 300 people. From a sample of 300 people living in your city, you ask questions whether or not they are in favor of a new duck tendency in the area. Remember, the sample is you talk to 300 people, 60 of them is in favor of it. So if you want to know the proportion for this, the 60 who said yes divided by 300 would be the proportion. So that's how we define proportions. It's like you already have the whole sample, the whole sample, the n, like 300, or, I take an example of 300, and you count the answers. So the proportion 60 divided by 300, that would be 0.2, for example, or 20%. So we can say that 20% of people surveyed are in favor of a new Dunkin' Donuts in the area. But we remember we said P hat, we call that sample proportion. You see, sample proportion is P hat. So it's like you take multiple samples and you ask questions. At the end, you see the distributions of sample proportions. Remember, it's symmetric about the mean. We know that 68% About 95% of the data will fall within this area, as close as possible to the population. But the idea is that you run multiple samples. You take multiple samples from the population and you ask each of them questions. And at the end, you combine all of this. So that's what we do here. And again, we can do it with only means, you take samples from a different sample from the population. Now, you see my questions in terms of proportions. 300 people survey, 60 answers yes to a questions, and then maybe 255 surveys 26 answer yes to the questions, and we see we combine them all. We make a sampling distribution of the samples. But now proportion means so sampling distribution of the proportions. For this one is sample. Instead of doing proportions, we can take different samples. Suppose in a classrooms, I ask students to conduct a study about a new latte in a coffee shop. So they go out there and ask people questions. They come up with their own samples, and then at the end, I combine all these samples, so we make a sampling distribution of the samplement. So it all depends on what you do. You see, for the variance, it's mostly skewed either left or right, but which is different. Let's see very closely and know that this type of distributions we can discuss about, because you see for the symmetric, not sure, we're gonna use it here, but remember when it's symmetric about the mean, then we use really the normal distribution. So sampling distribution of a statistic, the sampling distribution of a statistic, such as a sample proportion or sample mean, is the distribution of all values of the statistics when all possible samples of the same size uh, and are taken from the same population. So the sampling distribution of a statistic is typically represented by as a probability distribution in the format of a probability histogram, formula or tables. We said the same here for the sampling distribution of a sample proportion, which is a distribution of sample proportion or distribution of the variable p hat. Remember, we talk about p hat is the equivalent. It's like you're talking about x bar, right? With all samples having the same sample size, and taken from the same population. So the sampling distribution of the same sample proportion is typically represented as a probability distribution in the format of a probability histogram formula. And as a notation for proportions, we need to distinguish between the population proportion P. Okay, P is the population proportion. It's like for us. Remember, for us, if we construct a small table where we said, all right, so proportion, population, sample. So for us, remember, if we do mean for population is mu, and is a mean for sample is x bar, right? If you do variance for population is sigma s square is s square. If you do standard deviation, I'm trying to make more as much as possible. If you do standard deviation, it is sigma or s. If you do proportion, for proportion, we only do P, and here we do P hat. Okay? So that's what if it's about sample, then it's P hat. N is sample size, capital N is, like sample size for us. Yeah, if it's sample, then it's capital N. If it's population, capital N. If it's sample, N. So etc. All right. So P hat is P with that hat symbols are used above the letter X bar or is to express statistics. Behavior of the sample proportions. Again, the distributions of sample proportion tends to approximate a normal distribution. Sample proportion target the value of the population, proportion in the sense that the mean of all the sample proportion P hat is equal to the population proportion P. The expected value of the sample proportion is equal to the population proportion. Sampling distribution of the sample mean is the distribution of all possible sample means or the distribution of the variable x bar with all sample having the same sample size and taken from the population. All right, so we're gonna have a chance to talk about it. Remember, in terms of behavior for sample means, the distribution of sample means tends to be a normal distribution. The sample mean targets the value of the population mean. Sampling distribution of this sample variance is the distribution of sample variance, like S square, with all samples having the same sample size and taken from the population, the same population. So those are the formulas. Remember, we did those before. This population variance is this formula, the second one, but if you take the square roots of it, remember, this one is the square roots of the variance. If you know the variance, you can only take the square roots of this one. Next would be, behavior. The distribution of sample variance tend to be a distribution skewed to the right. The sample variance target the value of the population variance. But I think there is one note I didn't add before the exercises. I'm going to just copy them because the estimators, you really need to have an idea of how the estimators works. I would prefer to put them before the exercises. So we cover all these definitions first, and then we can focus on doing exercises. Now, the estimators. I don't know if you heard about it before. In terms of estimators, we said estimator is a statistic used to infer or estimate the value of a population. So what we want to show here is about unbiased and biased estimator. So for unbiased estimator, is a statistic that targets the value of the corresponding population parameter in the sense that the sampling distribution of the statistic has a mean that is equal to the corresponding population parameter. So that's for the unbiased. So these statistics, in terms of for unbiased estimator, these statistics are unbiased. That is, they each target the value of the corresponding population parameter, like with a sampling distribution having a mean equal to the population mean. So for us, you see sample proportion P hat, the mean X bar, the variance S square. So those are all about the sample. Remember, these are about the samples. Now, we said also for the bias, the unbiased and the bias. So the bias statistics are biased. That is, they do not target the value of the corresponding population parameter, right? So what they focus on is the median, the range, and the standard deviation. So very important notes on these. The sample standard deviation do not target the population standard deviation sigma, but the bias is relatively small in large samples. So S, which is the standard deviation of the sample, is often used to estimate the population standard deviation, even though S is a bias estimator of sigma. So, of course, I know that sounds a lot of work, but why sample with replacement? Usually we do it with replacement because for if you, well, some reasons like when selecting a relatively small sample from a large population, it makes no sense difference whether we sample with replacement or without replacement. Sample with replacement result in independent events that are unaffected by previous outcomes, and independent events are easier to analyze and result in simpler calculation and formulation because we covered these before, in the other video. So I strongly advise you to go back and see when what it is when we talked about dependent and independent events. Now let's start doing some examples. In these examples, so we're gonna start very quick on it, right? Let's do these examples. Um, they said use the sample the same population 49459, assume that size of n, because what happened with sampling distribution of the sample mean. So for this we need what you need to see here, we can use from the same sample taken from the population, okay, another samples to make sense. Okay, that makes sense to you? We're gonna just continue doing it. Okay. Now, let's try it this way. We're gonna do the first examples in these sections because, as we said, we talked about it, is doing the sampling distribution of the sample mean. I'm gonna just look for it. Um, okay, sampling distribution of the sample mean. Give me 1 second. Have some definitions. I was looking for you from the book. Yeah. So sampling distribution is the probability distribution of a statistic or a sample statistic that is formed when random sample of size n are repeatedly taken from a population. If the sample statistics is the same mean, then the distribution is the sampling distribution of sample mean. So I don't know if that makes sense because I wanted to use a definition that is more relevant. Every sample statistic has a sampling distributions, right? We can, for us, there are different ways of saying it. If we do the sampling distribution of the sample mean, you can have a different standard deviation when there is a sample size, a sample taking from it, a size taking from it. So meaning for us in this case, the mean of the sampling distribution would be equal to the mean of the population, but for the standard deviation of the sampling distribution, it would be equal to the standard deviation over the square root of n because we take this randomly. Now, let's try to do something. I'm gonna just copy these two, probably put them somewhere because I don't want them to be in our exercise. I'm gonna just copy them and put them here. When you have a size n. Okay. Now let's go with the first example. The first example says, the goal here is to find the value of the population variance. Let me make this one smaller because that would be very helpful to have enough space. Because what they ask us to do here, let me put it 14, maybe 14. Let's do 16. All right, is that okay? Okay, all right. Now, the first thing to do, remember variance? This is what we said population variance is sum of x I minus the mean square over, it's just only n because, no, that's a sample. Because we're doing for the sample, we're going to do n minus 1, if that's okay with you. Okay. Do we do n minus 1 or we're gonna just do n? Because if we deal with the population, you need to say it's n only n, not n minus 1 then, because we're doing populations. Okay, now you also need to find the mean. What is the mean? Mean mu. Remember, mean, you need to add all your data and you divide it by n. So what are the data you have? These are the data because you have 4 plus 5 plus 9 over how many data you see? 3. So 4 plus 5 is 9 plus 9, 18 divided by 3 is 6. Yeah, we find it. Now, remember how to find the variance? We said if you have your x values like 4, 5, and 9, to find the variance means you need to subtract the mean from each data and you raise by 2. So you do 4 minus the mean, power 2, 5 minus the mean, power 2, 9 minus the mean, power 2. Frankly, you said that should be 4 if it's okay. I'm going to do it this one because it's not that difficult, but usually we're going to do it with calculator. That would be 1. That would be 9. Remember, raising to power 2. So that's how we end up with sum of xi minus the mean square. Xi minus the mean square give us what? 14. So for us, variance, the goal is to find the population variance. What is the population variance? It's sigma square equals sum of xi minus the mean square over n. So we said sigma square equal 14 over n. Remember, n for us here is 3 because we have n equal 3 data, not the size 3. That's two different questions. Now, once you do 14 divided by 3, it gives you 4.67. Okay, so we're going to have 4.67. So this is the first questions we answer part A, which is find the variance, population variance. Now, what they ask us to do, there is an examples in the book, but they said construct a similar table representing, or we could say construct a table. I'm not gonna say construct a similar table. We said let's say construct a table because representing the sampling distribution of the sample mean. So now the goal, they said use sample size 2. That means you have 3 different data. Let's say for B. If I want to construct, a tables, first of all, my goal is to see how many combinations of size 2 we can do. Okay, let's see the sample. This is the samples we're gonna do. Okay, let's try some samples. You have 3 data. You can do, because they said do size 2, we can combine 4, 4 as one. They said we can do it with replacement, right? So we do 4, 5, 4, 9. Now we're done with 4. Let's do 5, 4, 5, 5, 5, 9, or let's do 9, 4, 9, 5, 9, 9. So how many you see in total? How many samples you see here? We can count. Yep. 9 of them. But there are some repeated ones. Now, how would we proceed? For this one, remember, for each of them, you need to find the mean. So what is the mean? Remember, if you do, because that's a long exercise, I'm gonna do only this one, then you know how to do the other ones. 4 you divide 4 plus 4 divided by 2 is 4. 4 plus 5 divided by 2 is 4.5. 4 plus 9 divided by 2. Yeah, 4.5. 13 divided by 2 is 6.5, right? 9 divided by 2, 4.5. 5 plus 5 divided by 2 is 5. 14, is that 14, right? 14 divided by 2 is 7. I'm hoping I'm correct with that. 13 divided by 2 is 6.5. That's 7 again. And 9 is 9. So those are the means. Okay, we do the means, we know the samples, we know the means. Our goal, they said, construct a table representing the sampling distribution of the sample variance. The big problem, we need to do the variance, not the mean again. So to do the variance, variance is sum. So that means for us, it's like we do the first x minus the mean, power 2, plus the second x minus the mean, power 2. Whatever we find, we must divide it uh, by n. Okay, for us, n minus 1, that means 2 minus 1 is going to be 1. Okay, so that would be a 0. Okay, remember for us what we do here, the first x minus the mean square, because we do this one, over n minus 1 because we're dealing with samples. So 2 over 1 is 1. So that's why I don't, when I do the top part, it's give me only 0. Let's try the next one. We do 4 minus 4.5 because the mean is 4.5 plus 5 minus 4.5 square. You see, doing this twice like this, I believe the answer must be 0.5. Let's go with the next one. We do, oh, no. We skip. I need to have more space. We have 4 minus 6.5 square plus 9 minus 6.5 square. When we do this part, it gives us 12.5. And if I want, I can, 5445 is the same if you understand, because this one would give me only 0.5. Okay. 55 is the same, it's gonna give me 0, if you agree. Okay. 55 will give me 0. With the 75, probably this one will be different, right? Because we do 5 minus 7 square plus 9 minus 7 square. What is this one give us? The 7? The 7 would give us 8. Now, 9 minus 6.5. 5 minus 8. So we know what is this one give us. The third one give us 12.5, right? This one with 7. 7 is the same like the previous one where we find only 8. And the last one, remember, that would be 0. So how do we have it? I can copy paste again just to continue, and you're gonna see the work we're doing. Okay, so because after we do that, this is our table, because they said construct a table representing the same sampling distribution of the sample mean. So that's what we do. Then combine values of that are the same. Which one are the same? Okay? So if you want to construct a table with those the same, remember what we got here is a sample variance. Now, if I want to see those that are the same, let's continue with the same exercise, except I would remove that table for now. The table is on the first side, so please feel free to try to do it. Okay. Okay, this is what happened with that table if we continue. The goal is to combine duplicates because they said this is the part we're gonna answer. Okay, we're gonna write combine values that are the same. Combine values that are the same. We said, oh, remember we're doing the samples, right? Sample variance. Sigma square meaning um, they are the same. I think if you look, we had zero. Of course, we find zero. After zero, there was a zero point 0.5 repeated. We have zero point 0.5 how many times? We're gonna check it. I think we have an 8 and we have a 12.5. Let's go back and check what we find in the table. You know, let's see the frequencies. How often do we find zero? So we can either call it frequency or, right? So how often said how often? Let's call it probability. How often? Frequency. How often do we see zero? I believe we find zero, one, two, and three. Three times. We find zero three times. Or you can say 3 out of 9 because we have 9 if you want to express it. How often do we have 0.5? 0.5, we had it twice. This is 0.5 here and 0.5 here, so we got it twice. Okay, I think, I don't know what's going on, but I think it's freezing a little bit. I'm just waiting, expecting this gonna change a little bit, but if it's freezing, it's freezing, okay? I'm just waiting for it. Okay, finally. Oh my God. Okay. Let's hope the problem is solved. We said 2 times. And 8, I believe 8 is 2 times also. And the other one is 2 times. So those are the frequencies. Those are how often when we construct this variance, sample variance, we find the same answer. So because that was the goal, the questions was construct a table representing the sampling distribution of the sample mean, then combine values of that are the same. So find the mean of the sampling distribution of the sample mean. So what we mean by that, remember part C, find the mean of the sampling distribution of the sample mean. So mean sample variance. So mean of S square. Remember how to find mean, right? You need to multiply everything you find with the frequency, right? So let's say instead of adding them, I don't want to add them. So because I find 0 and I multiply it with 3, plus I find zero point 0.5, I multiply it with 2, I find 8, I multiply it with 2, I find 12.5, I multiply it with 2. So count how many sampling do we have? You go back in the previous tables. How many samplings do you see? Please. Yeah, we have 9 samplings. So that's very important. So we have 9 samplings. Okay. So all you need to do, compute these probabilities. Okay. And at the end, the mean of S square would simply be, when we do everything, it gives us also the same thing. So like 4.67. See? We find exactly the same answer as the previous variance, the mean variance we found, right? We find the exact same one. Now, the question based on the answer is the sample variance and unbiased estimator of the population. Yes, because the mean of the sampling distribution of the sample variance is equal to the value of the population variance. See, you're looking for the mean of the sampling distribution of the sample variance is equal to the population variance. It's the same. So the sample variance target the value of the population variance. So we can see it that way. Or, there's a different way to say it, but of course, it is true because the mean of the sampling distribution of the sample variance is equal to the population variance. All right, this is how we're going to proceed to do all of this because I hate doing the same exercise multiple times using I mean manually. Otherwise it's better we do with Excel. In a different video I would go ahead and do this because look, if n if in the previous exercise we had only three data give us 9. Okay, 3 data give us 9 different samplings. Just imagine in number 3 how many we're gonna have. So let's say here, when they give you, 1, 2, 3, and 4, now you need to do combinations of 2 each time. Just imagine how many data you're going to have to do this, because this would be a lot. Okay, this would be a lot when you do it, because you're gonna find about 16 samples, right? You're gonna have 16 in totals, right? Because you're gonna just to show you, you're gonna do 2, 3, 2, 5, 2, 2 first, 2, 3, 2, 5, 2, 9. Now you're gonna do 3, 2, 3, 3, 3, 5, 3, 9. Then you need to do 5, 2, 5, 3, 5, 5, 5, 9. You do 9, 2, 9, 3, 9, 5, 9, 9. So if you count, that would be, um, you know, 16 of them, and you should do exactly the same thing we just did. That's why I leave you. I said, yeah, I believed in you that you can continue doing the same work. Maybe looking at this one as it is a little bit different, because in this example, they said when two belts are randomly selected, the sample space for genders is boy boy, boy girl, girl boy, or girl girl, where B is boy and G is girl. So assume that these 4 outcomes are equally likely. Construct a table that describes the sampling distribution of the sample proportion of girls from two births. So one thing you need to remember here, for each outcome, there is only one possible. So if you have your sample space, all possible solutions are either you have two boys, or you have one boys, one girls, or you have one girls, one boy, or you have two girls. Oops, sorry. So for you here, what do you think the probability would be? It's 1 out of 4. You cannot have all four at the same times. So it's 1 out of 4 scenarios that can happen. So for us, probability is now knowing the probabilities, you can find you one. So remember we said you can have boy boy, boy girl, girl boy, or you can have girl girl. So if you try to construct a table as they ask you, because those are the outcomes, you know, uh, like if you're interested on only girls, number of girls, so number of girls here, there is zero. Here maybe only one, here one, or here is two. So that's what you expect. Now, in terms of proportion, because we covered what is proportion already, right? Proportion. What do you think the probability of having a girls here? Because two babies born, so it's gonna 0/2. That's zero. 1 out of 2, obviously it's gonna be 50% chance. And 1 out of 2 would be 50% chance, or 2 out of 2 is 100%. Is 100%, right? Because you are certain that both of them would be girls, so it's one. All right. I tried to construct a table to explain it better. But for the probability, we knew the probability already, right? Probability for each case is 1 out of 4, 1 out of 4, 1 out of 4, 1 out of 4 for the probability. So how often do you see this happen? Because they said, oh, construct a table that describes the sampling distribution of the sample proportion of girls from two births. There's the sample of the same proportion equal the proportion of girls into births, So what you see here for this one is a little bit different. Okay. So for us, we see that these probabilities you have for both of them twice. The mean of the sample mean, we can see it. Okay. Remember, probability proportions is 50%. No, probability, sorry, is 50%. So because they have equally likely to result the result the girl or the boy. So population proportion is 1/2 or 50%, right? So that's what you need to see. But if you want to do the expected values, all you have to do is expected values would be, the first one is 0. If you take the 0 you find here, multiply it by the probability 1/4, and you take the second probability also, all right? What it is, you do point. It's 1 times 1/4. That number of girls again, 1 times 1/4, sorry. It's like 2/4 if we want to do it this way, that's fine. And the last one would be plus 2 times 1/4. Okay, so that's how we got 0.50% for the population proportions. All right, so the mean of the sample proportion is 50%, and the population proportion of girls is also 50%. So yes, the same proportion is an unbiased. So I'm gonna let you because as I said, those takes forever to be done. I would let you to enjoy and let me know how do you come up with number five in the comments or send me an email. I'll see you in a different video. Take care.